Hello, everyone. Sorry, I'm a bit nervous here, but I'll try my best to convey what I want to convey here. Okay. Hi, I'm Vagisha. I'm so glad to be here and honored. Last time I was here back in Athens. Now I'm here again, alone. I'll be presenting my talk on AI-powered threat detection with SuriCata. Before we go into the technical details, a little bit about me. I'm a software engineer at Red Piranha developing security solutions. In the past, I had the opportunity to intern with Outreachy, and I worked with SuriCata on the project SuriCata update. I hold a postgraduate degree in data analytics and AI. I have an expertise in machine learning, data, big data analytics, intrusion detection prevention systems, VPNs, asset management, and databases. I'm based in India. On the personal note, I love reading, traveling, and capturing moments of places I visit. You can contact me if you want in the details I've mentioned here. So here's a talk outline of what we'll be covering today. First, we'll be looking at the traditional threat detection approaches that are used for securing a network. Then we'll see what are the current challenges with those approaches. We'll see how we can leverage SuriCata and AI for advanced threat detection. I'll be presenting my overall high-level framework for advanced threat detection, and we'll go to two use cases to see how the framework works. The first one we'll be seeing will be DDoS attack analysis, and the second one we'll be looking at will be the classification for encrypted traffic. And at last, we'll see how this works in the real case scenarios for deployment purposes. So traditional approaches for threat detection. Traditionally, we use these three approaches for threat detection. The first one is signature-based detection, which primarily relies on the predefined signature and rules to detect known threats based on specific patterns. What is a drawback with it? It works very well, but in case you don't have a signature that matches an attack, a threat, you might miss certain attacks. The second one is anomaly-based detection, which establishes a baseline from normal behavior based on the historic network traffic and patterns. Any deviation seen away from those baseline is marked as a potential threat. So in this case, there can be many false positive alerts triggered in case your network changes or it gets scaled at high level. The third is the heuristic-based detection. So it uses a proactive approach that uses behavioral algorithms to detect suspicious activity based on certain patterns. It can get a little difficult to detect based on heuristic detection if we see complex threats. So what is the challenge with these approaches? Anomaly-based detection, signature-based detection, both of these generates alerts and normal data. So as the network traffic grows, a huge volume of data and alerts are generated from the raw traffic. The security analyst has to review those alerts manually to see whether it's actually a genuine alert, or it can be a benign, it can be marked as a normal traffic. It also triggers a lot of false positives because our traffic network seems to change very quickly. Also, sometimes a threat comes in, and we need rapid detection and response, so real-time analysis is required, which analysts cannot keep up with. Also, these approaches have limited contextual information about asset values, user information, and other logs. So these methods cannot overcome these challenges. So how we can enhance threat detection with SuriCata and AI? Now, SuriCata generates raw traffic, which is known as JSON data, which consists of multiple events such as alerts, TLS, RDP, SMB, HTTP, etc. We can use those, even though SuriCata generates this rich event, it still needs deeper analysis to understand the network behavior. So here is where AI comes into picture. We we can run ML, machine learning, and deep learning baselines on top of this raw traffic that is generated by Suricata to detect and classify network. We can, the machine learning models can learn behaviors across the networks, the patterns. It can classify the traffic to apply policies into it, and overall it can automate the security posture of the system, of this network. This is a framework that I'm proposing for the advanced threat detection. So these are the steps. I'll walk through it, all these steps in details in the later slides. The first is the data collection. So you can use Suricata or any other IDPS tool you want to generate network traffic. You can enrich those logs with the help of other tools, maybe, or other logs, maybe firewall logs, user logs, or any other logs. And once you have all the data collected, it needs data preparation, because the data that is generated by Suricata is in textual format, and our machine learning based models cannot understand those textual, so we need to convert the data. So the first step is data cleaning, so I'll go through all these steps in detail. So data cleaning, we need to perform feature extraction and engineering. We need to do data normalization to standardize the data, and lastly, the feature selection comes in. After that, we split the data into two parts, training and testing. Training set is required so that the machine learning models can understand those patterns, understand the patterns, learn from the behaviors, and the testing data comes into place once we have unlabeled, we want to give model the unseen data and perform evaluation on the data. So the first use case that I'm going to use here is DDoS attack analysis. We'll see how the anomaly can be detected for the DDoS attack, because it's a well-known attack that everyone understands. The first step is data collection and ingestion. So for my use case, I use this data set, CIC IDS 2017. It is a publicly available data set. I have linked down the URL from where you can get the data set in case you want to play with it. So also they have a research paper which I've mentioned the reference of it. So this data set, so what these people did was that they created an environment where they ran different attacks on a 7-day interval of a week. Each day they performed different attacks. So first, maybe on Monday they performed FTP, and then SSH. On Tuesday, DOS, Heartbleed, web attack, infiltration, botnet, and DDoS. For my use case, I chose DDoS. So DDoS was performed on a Friday afternoon. So I picked up the Friday working hour.pcap from that data set, which consisted of a normal activity and the DDoS attack type data set. The total size of that PCAP was around 8.3 gigabits. So how they performed DDoS in their environment was they used this tool Loic. So there were 3 attackers with 3 windows, and they targeted one victim Windows Ubuntu server with the IPs mentioned here. So after I used the PCAP, what I did with the PCAP was I ingested the PCAP using Suricata's offline PCAP mode and Unix stream, and the data was directly ingested into MongoDB. So I used MongoDB for this purpose. You can use whatever, whatever database you want or data source you want to store the data into. After the data was inserted into the Mongo database, the count of my documents came around to be 750K documents. The next step was to perform data processing. So for the data processing, the first step that I did was flattening the nested data. So Suricata Eve data has a lot of nested data structures. So I had to flatten the structure. So for example, for SSH, we have SSH version. So what I did was flatten the structure and renamed it to SSH_version, or event, or maybe alert signature ID into alert_signature ID. So all the fields were flattened into one single document. Then the missing values were handled using mean computation. Data was aggregated using flow ID. So different event types have single flow ID. Based on the flow ID, I aggregated the data so that it can be aggregated into one single document. I removed non-informative fields that was not required for my training purposes, and it could lead to overfitting of or underfitting of the model, for example, and was not very good for the model training purposes, for example, MAC addresses, IP address, etc. I removed duplicated columns and correlated fields from the data. For example, okay, so and after that, because the data set had a lot of majority classes of normal traffic rather than the attack DDoS type, so I handled the imbalanced data by resampling the data. The method I used here was a random undersampler for balancing the data into equally into two classes. The next important step before we pass this data to the model is feature engineering. Feature engineering is really important for our model to perform effectively and efficiently. Because the Suricata data consists of highly textual format, so for the DDoS purpose, the two methods that I used was one-hot encoding and label encoding. So you can see the flow state, HTTP protocol, direction, event type, and protocol was converted into binary columns because it had less number of fields inside it. So that's why I used one-hot encoding. And the label, which was marked as 0 and 1, was a label malware, and normal was a label encoded with 0 and 1 values. The next step was to compute new features out of what we already have and transform them. So I computed flow duration. So flow duration was computed from flow start and end timestamps. And then all the timestamps were pre-processed into Unix time for easier understanding and analysis for the model. Then I aggregated and fetched new features out of what we already have. So for example, I computed total bytes, total packets, average packet size, packet ratio, and so on and so forth features from the flow matrices that we already had. Then inter-arrival time, that was the standard deviations, and average deviations were derived from the packet arrival times. All the features that were derived from this, the Suricata, are mentioned in the table. So for flow, I have used the ones you see right next to the flow for HTTP. So yes, for DDoS attack, they performed the data set that I picked up. They performed the DDoS by flooding the victim with TCP, UDP, and HTTP protocols. So what I did was, when I was doing the data analysis part, I saw that there were around like thousands and thousands of records for HTTP events. So I picked up those majority of HTTP fields for this purpose, and I use HTTP port, content range, content start and end, HTTP protocol, HTTP length, and status field from those fields. And then I used alert and miscellaneous. So these feature selection basically is done based on the use case that you're working with. And the domain knowledge of the attack that you're performing. So for my case, it was DDoS. That's why I picked up those. And the model actually performs differently with what features you are picking up, selecting for your data set. So you have to play along and see how the model is performing. For my case, I use these features for this use case. The next step before we train the model was to normalize the data. So for the normalization, I used min-max scaling technique. It scales the data into the range of 0 and 1 using the fit transform method. And then because the data was highly spatial, so I had to reduce its dimension. I used principal component analysis, PCA, to reduce the feature space, and only so that it only highlights the important components of the data. Then next step I used was to perform feature selection by using feature selection techniques. For my case, I used random forest and recursive feature elimination and calculated top important features from all the features that I manually picked from. So the top 15 features for random forest is shown on the left-hand side, and you can see the protocol. The event type HTTP destination port, which was 80 in my case, and these were the topmost features that that had the most important value. And the recursive elimination, the recursive feature elimination only gave about around 10 features that were of highly important values. Then comes the model training. So for this case, I used supervised and unsupervised learning algorithms. For supervised, I used quadratic discriminant analysis, machine learning algorithms, which were quadratic discriminant analysis, Gaussian naive Bayes, random forest, decision tree, AdaBoost, KNN, and deep learning algorithms like multilayer perceptron, convolutional neural networks. We'll see how all these perform later in the later slides. For unsupervised learning, I used isolation forest, local outlier factor, elliptic envelope, and deep learning algorithm, which was autoencoder. So here's the evaluation metrics for the supervised machine learning models. You can see here that the random forest and the multilayer perceptron was the one giving the highest accuracy, which was around 99.92 and 99.94%. So accuracy is the total score that comes out of the whole, how accurately the model is performing. In terms of recall and precision, which tells us about the positive and negative classes, how well they are performing, for that you can see decision tree and I think, yeah, nearest neighbor were the ones which gave the highest recall and precision. Logistic regression, the naive Bayes and the QDA were the ones which had lower accuracy in other matrices from the graph. You can see it was coming around 96.15%. Not low enough, but as compared to other models, it was low. Moving on, the convolutional neural networks was the one which performed because, of course, it's a neural network, so it was the one which performed most accurately. The test accuracy came out to be 99.9%, and loss function was also very low, which came around 0.03%. Here are the evaluation matrices for unsupervised models. So unsupervised models comes into place when you don't have label. For my data set, because I picked it from the data set, they already had the labels with it. So for my case, I did have the labels, but when we're dealing with real-time traffic, we don't have labels. So unsupervised models, based on the features that I selected, performed a bit low. You can see elliptical envelope was the one giving 71.2 low accuracy as compared to the supervised models. But yes, this was the results of the unsupervised models that came out to be. This is the result from for the autoencoder. So what autoencoder does is that it takes in the input, encodes it, and then passes it to the decoder to regenerate the output as closely as the input, and see if there's any deviation from the input, it marks it as an anomaly. So on the figure 2, so you can see there are the anomaly scores. I considered 95 percentiles. A red dashed line is marked as the anomaly threshold. So 95 percentile was considered as the anomaly threshold. And all the deviations going above 95 percentile were marked as anomalies. Figure 3 gives us the reconstruction graph. So the top row you can see were the original graphs that were constructed, and the bottom row were the reconstructed graphs. So you could see minute deviations if you compare the original and the reconstructed graphs, and those deviations were marked as anomalies. Okay. So the next use case that we'll be seeing, this was all about anomaly detection. The next use case we'll be seeing will be classifying the encrypted network traffic. So why do we need to categorize network traffic? It helps us identify application types. So once the data is collected from the internet, raw network traffic is generated, and we want to classify into multiple classes based on the application types, out of which one can be anomaly. We needed to detect anomalies to enhance our network security posture and to optimize network performance in case we might want to apply certain policies on those applications. How traditional approach works with classifying network traffic, and what are the challenges with it? So first is the port-based identification. It uses standard port numbers to identify traffic types. It can be ineffective as many applications now are using dynamic ports and also using encrypted protocols. The second is deep packet inspection. In port-based, you only use standard port numbers. In DPI, you inspect the packet headers and the payload or a detailed packet analysis. It can be highly computational. It can have high computation cost, and it can be also a bit tricky when it comes with encrypted packets. Where does SuriCata and ML comes into play when we want to classify encrypted traffic? SuriCata gives us metadata, highly rich metadata, which includes TLS informations, SNI certificates, IP address, ports, protocol headers. We can use those fields and pass it to our ML models so that the model learns from those features, identify the patterns and behaviors, and classify the network into different classes, application types. So, for example, TLS handshake features that can be used are cipher suits, certificate information, SNIs, flow statistics like packet sizes, inter-arrival times, flow duration, connection behaviors like frequency of connections, ports, and protocol data. So for this example, the data was collected from USTC TFC 2016 dataset. It is available in Kaggle. I have provided the link if you want to play along with it. It was released by Security Laboratory of University of Science and Technology of China. There were 10 categories of malware. In the table, you can see on the left-hand side, these were marked as the labeled data, as the malware type traffic. And on the right-hand side, you can see the normal traffic, the 10 classes of the normal traffic. The PCAP size was around 3.7 gigabits. In the same way I did with a DDoS dataset, I ingested the document into the Mongo database, and the count of the documents was around 1.1 million documents. The event types that were logged with these datasets were alert, anomaly, DNS, file info, flow, FTP, HTTP, RDP, SIP, SMB, SMTP, SNFP, and TLS. So in case of DDoS, I knew that the feature engineering and features that I want to focus on were HTTP types. But in case of classification with multiple classes, I cannot use one particular event. Though I know that the data that I'm trying to classify is encrypted data, so I focused more on TLS. But with that, I also picked up other features as well. For encoding here, I used one-hot encoding in a similar way I did with DDoS, label encoding. But I also performed target encoding on top of that for some of the features, because it was highly contextual textual data and had a lot of categories, and I couldn't encode into one-hot encoding. New features were computed from the features that we already had, like flow duration, timestamp, aggregate matrices, inter-arrival time, standard deviations of packet sizes. And again, the manual feature selection was performed. These on the table, you can see the features that I manually picked up for my model training. Next comes the model training for multi-classification. Machine learning for encrypted traffic classification can be performed either by behavioral analysis, so we can use unsupervised models to detect anomalies for encrypted traffic, or we can use supervised and deep learning models to classify the encrypted traffic. In my case, So for the machine learning algorithms, these are the results that came out to be. So you can see decision tree was performing nicely for here for our classifications. You can see it was predicting with high accuracy for these classes. Logistic regression not as good as decision tree, but still was giving good results. K nearest neighbors was the one which had the most highest accuracy and the evaluation matrices. Random forest was also giving very good results. AdaBoost and Knife Base were the ones which were struggling to identify the classes. You can see, for example, for AdaBoost, BitTorrent was not at all was not able to identify itself. Similarly, with Knife Base, you can see we were not able. The model was not able to classify geodo attack type. This was the result from MLP. MLP was also, again, performing really well with the multi-classification. QDA was, again, struggling with classification. And then gradient boosting, it was also performing really good with the classification. Here's a comparison of all the models. You can see, so the K nearest neighbor, multi-layer perceptron, and CNN and gradient boosting were the ones which had the accuracy around between 91 to 93%, which was the most highest that we achieved. Knife Base and AdaBoost were the ones which has a little low accuracy, around 62 and 64%. Here are the results from convolutional neural networks. So the test accuracy that was achieved for this was 93%, and the loss was a bit higher in this scenario, which was around 5%. Maybe if I had time, I could have played along with some, certain features and see how our hyperparameters and see if I could reduce the loss here. But yeah, this was what I could demonstrate here. These are the results from autoencoder. Again, it did not perform as good as a two-class classification, but yes, this. So bringing it all together in deployment, how this works in real-time applications. So you have different devices connected to the network, right? And it generates raw network traffic. You can use SuriCata to capture that traffic, or you can use PCAPs if you know what use case are you going to work with in identifying anomalies. Whatever tool you use, it generates traffic, and you can store that offline data into any of the database you want, maybe CSVs, database, JSON, or anything else that you want. Then you perform data engineering based on your use case. So in my case, I used a combination of all events. In your case, if you want to perform infiltration or exfiltration, you can use certain event types to run baselines on. So in the similar way, you perform data preprocessing, feature engineering, feature selection. And then after you split your model, after you split your data into training and testing data, you run baselines. You pick from the variety of supervised and unsupervised models that you have. So when it comes to real world, you don't have labels. Because I picked the PCAP, and it did have labels, so it was easier for me to demonstrate here. But when it comes to real world, you don't have labels, right? So what you can do is you have multiple options, but either you can run unsupervised label, and you can get pseudo labels out of which, based on the clustering or anomaly scores. You can use those labels and then retrain your model on supervised algorithms. Or maybe if you have the domain knowledge of how domain knowledge based on your SOC or analyst, you can manually mark the labels. Otherwise, unsupervised works the best. After picking up the baselines, you train your model using the ones you have picked up, and then you use that trained set and on the trained model and perform threat detection or any other use case that you want to work with. For this case, I've written finding anomalies here. So the anomalies are Once you have the trained model, what you do is you capture the live traffic that comes from the SuriCata, and it is again passed, that's unseen data, it's without the labels, and it's again passed into the trained model, and hence the evaluation is performed. Now, sometimes what happens is because your network can change if it scales at a higher extent, or anything can change. So what you have to continuously monitor the network and perform continuous learning on the model. Also, you have to see if the model is if you have picked up certain algorithm which is not performing as good as maybe the other one, you can change the algorithm and see how does it performs. Or if the model is giving a lot of false positives or certain false positive, you have to change the action and mark it as normal data or anomaly data, and give it back to the model to retrain or fine-tune the model. Yes, so that's how it works in deployment. Yeah. I hope it was helpful for you guys, and you can see and play along with it and see how it performs for you. So yeah, that's it. Thank you so much. Any questions?
Test? Okay. I may have an initial question. Is this work somewhere publicly available? Like, can someone follow up on this?
Not yet, but I'm planning to pull it to my GitHub, so I'll do that and post it on the forum or anywhere else. I can share it with you.
Okay, thanks.
Yeah.
Hi, Leo from Graphistry. So first of all, this is a really fun talk to see. Is like seeing all the kind of traditional ML methods one by one. So that was just like, as an introduction, that was very nice, I think, for the community. What I found interesting is that you were using these kind of public test sets. So I think for an academic scenario, like not a non-commercial, but an academic scenario, I think that's absolutely appropriate. But for use in a real world by, let's say, practitioners here, I was curious, did you do any cross-validation to make sure you're not overfitting on these academic test sets? Like where we're using external data sources to make sure any individual trained model result actually generalizes to non-cherry-picked data?
Yeah, so for this demonstration, I used academic data set, but in our company, we are using the real-time traffic that is coming from the clients, and we're running unsupervised models on top of that. And so what we're doing is we are creating baselines based on the, based on the working hours. So if any deviation or any alert is triggered, or the model is giving any anomalies apart from the working hours, maybe if someone is trying to SSH into the network, not under the, so model is trained, say, for example, in 2 hours baseline, and then 4 hour baseline, and then 6 hours and 8 hours. And anyone trying to SSH into the system, apart from those working hours, so model itself identifies that as anomaly and mark it as an alert or an malware. So yeah.
So maybe phrasing a little differently, do you have measurements of generalization for if people did train on those data sets and tried to use your technique, what the delta would be?
I'm so sorry, I didn't catch that.
If you tried to, in the cross-validation, what would be the measurement of the delta of generalization?
No, I don't have that number.
Okay.
I'm so sorry, yeah.
All right, thank you. But again, great work. I really enjoyed it.